All right, morning everyone. So yeah, before we continue with the broadcasting, by the way, so we already released the Lab 1 solution. So as you can see here, usually for the ungraded labs like Lab 1, Lab 3, or so on and so forth, after the conduction of the lab teaching, we will release the solutions here so that you can check that. Of course, we always recommend you that first you try to solve all the tasks by yourself. After that, you check the solution to see like where you get wrong. And the recordings are released here. So we will also release the recordings of all the labs. Later on, we will also release the Lab 2. I think Lab 2 will be released today or tomorrow. And recall that Lab 2 is a graded lab, so that you need to submit to Zinc. Then for the graded labs, the solution will be released after deadline. So that's a few weeks later. All right, this is about the Lab 1. So yeah, please check the course website to see all the labs and the solutions in the future. Another reminder is about this. Yeah. Thank you for pointing it out. This flatten actually is a copy, it's not a view. So yeah, I mark here, and also I uploaded this updated slides to the course website. Yes, flatten returns a flattened copy of the array instead of the view. But that means after you change, you modify some values of the flattened array. Basically, the original array won't get changed. They are not the same data, which is, this case I think is a little bit confusing because as we can see, for all other methods which only change the shape or only rearrange the dimensions like reshape, transpose, expand dims, new axis, these methods all return the view, but only this flatten. Actually, it's also like try to reshape or try to rearrange everything, but this one actually it returns a copy. So yeah, try to like pay attention to this difference. Flatten is a copy. All right, so next we can have a review of the broadcasting rules. Broadcasting rules, we already finished the introduction of these rules. So recall that first we always need to try to compare the dimensions of the two arrays. If they are not in the same dimension or if they are not in the same rank, then we need to prepend the shape of the lower rank with 1 until they have the same length. So until as if they are in the same dimension. Then we compare the two arrays one dimension by one dimension to see whether they are compatible. We see that they are compatible if these two cases, one of the two cases is satisfied. The first, if they have the same size in the dimension. Secondly, if one of the array has size 1 in that dimension. Only these two cases we say, okay, they are compatible, and then the two arrays can be broadcast together if they are compatible in all dimensions. All right, so basically the first 3 steps is used to decide whether two arrays can be broadcast together or not. Then here is a question for you. Maybe you can have a quick thought. Do you have any other ways to restate the broadcasting rules? Only like referring to the first 3 steps. Actually, the main change will happen in the first rule. So any other ways, if now you restate the broadcasting rule, so that means you change the statement, but somehow you get an equivalent rule to decide whether two arrays can broadcast together or not. The hint would be, is there any way that we don't need to prepend the shape of the lower rank with 1? If we don't want to do this step, this step is somehow redundant, right? You always need to prepend so many 1s until like they have the same shape. But what if we just want to omit this step? We don't want to prepend with the 1s. Do we have any other ways to try to decide whether two arrays are broadcasted together or not? Any quick thoughts about this one? Yes, please.
I think we could just start from the right and see if at any place the two arrays' dimensions are different and none of them is 1.
Yeah,
So
yeah,
if that
yes.
happens, then it's not stochastic.
Right, exactly. Yes, very good. Yeah, it's very good that you can like quickly think about this equivalent statement. Yes, very good. Yes, what he said is exactly correct to restate the broadcasting rule. That is, if now we don't want to prepend the shape, basically we only need to compare the sizes from the rightmost. You do this right align, and then starting from the rightmost dimension, try to compare them one by one to see in all these dimensions whether they have the same size or one of them has size 1. And basically just stop at the lower rank array, right? Because for all the longer shape array, basically if we follow this rule, anyway you will prepend them with 1. And after you prepend them with 1, of course they are compatible. So actually we don't need to do this prepending. We're just starting from the rightmost to try to compare them one by one. So like for example, if we look at this one, so this pair 4, if we just take it as an example. So previously we just do this prepending, right? That is, if weight A has this shape, 15, 3, 5, and then B has such shape, 3, 5. Previously we do such thing is that we let A be 15, 3, 5, and then we prepend B with 1, so it should be 3, 5. And then we just try to compare dimension by dimension. But actually we don't need to do this prepending if we're just starting from the rightmost. If we're starting from the rightmost, then we do this right align, and we check that, okay, this dimension 5, 5 same size, and this dimension 3, 3 same size, compatible, and we just stop here, because for this array B, actually it does not have like one more dimension. So just stop here, and then we find that, okay, A and B, they are compatible in all dimensions, they can be broadcast together. So this is alternative way, equivalent way to state the broadcasting rule. It's very good. Then if we, according to this rule, then we can easily find pair 6 is not compatible. Like now A has this shape, okay, 16, 6, 7. B has the shape 16, 6. But note that we need to compare from the rightmost to this right align. So B, we write it in this way. And of course, this dimension not compatible, this dimension not compatible. So that's why for the pair 6, A and B cannot be broadcast together. All right, very good. So yeah, basically then you already fully understand the broadcasting rule if you can like easily think of this alternative way. Next would be how to use the broadcasting in practice, right? If we only look at these exercises, it's like that, yes, these exercises are interesting, but what's the real-world application? Like, is it only for fun to do these things? No, broadcasting actually plays a very important role in some practical cases. Actually, usually they are useful in simplifying the calculations, and we will use 2 real-world examples to illustrate their usefulness. The first would be how to center in an array, and we give a gradebook example here. So now, suppose we have a gradebook for 4 students. These 4 students, each of them have taken 3 exams. So basically now we store these scores in a 4 by 3 array. So each row is 1 student, each column is 1 exam, right? So all their grades, and let scores be this array. This means the first student taken the 3 exams get 1 point, 2 points, 3 points, and so on and so forth. Now what we want to do is that we want to center in such array so that we want to make sure, okay, now the mean score of each exam is 0. Then how to easily do that? Let's say first we try to compute the mean of each exam using the mean function across the first dimension. So let this score mean be scores.mean 0. And recall what is this 0? 0 means that we pass the parameter x is equal to 0 here, right? So here we omit the keyword argument, but actually this 0 means x is equal to 0. And hope you still remember when x is equal to 0, which direction we want to compute the mean. It's along the row direction, right? So basically that is if we arrange these scores to a 4x3 array, then after they score mean, we compute the mean across the row direction. That means for each exam, we get the mean score of the 4 students. And then we get this score mean like this. Of course, after computing the mean, now it's a 1D array, 5.5, 6.5, 7.5, means that for the first exam, the average score of the 4 students is 5.5. And for the second one, the average score is 6.5. For the third exam, the 4 students get 7.5 average score. Okay, why do we need to compute the mean? Because if we want to center such array, then of course we need to get what is the original mean, right? After that, we can try to renormalize it so that its new mean becomes 0. Okay, we already get this mean currently. And next we do this centering. We center the scores array by subtracting the mean. Directly, if you use the original array, subtract this mean, then after that, supposedly, you will get the 0 mean, right? And this step, we are using broadcasting. So we let the scores centered be scores, the original array 4x3, minus scores mean. And this step, of course, we are using broadcasting because if we examine the shapes, the scores is a 2D array. We know that the shape is 4, 3. And this score mean, which we just get, is a 1D array. The shape is 3, right? According to broadcasting rule, they are compatible in all dimensions. So that means we can do such operation. And after that, the score centers is this one. Know that this is already the centered array we want. That is now we center the original array so that the mean score of each exam is 0. You can further check it by getting this score center dot mean 0, and it will print 0, 0, 0. So this array is already centered. This is one usage of the broadcasting. So know that basically if you want to center in some array, later on you may want to center in your data or try to normalize your data, for example. Actually, you don't need to do like for loops. If you can use broadcasting, then you can easily using this one line of code to try to implement it and directly get what you want here. So any question regarding this example? Okay, great. Yeah, this is a warm-up example how to use the broadcasting in a relatively simple situation. The next example will be somehow a little bit more complicated. Is how to compute the pairwise distances. Suppose now we have two 2D arrays, x and y. Here x has such shape and d. Y has such shape and d. Note that they are both 2D arrays, and they have the same number of columns, but somehow they don't have the same number of rows. They have different rows numbers. Then, of course, we know x and y, they are not always broadcasting together, right? If m not equal to n and none of them is 1, then basically x and y cannot be broadcasting together. So yeah, this is the premise we need to know at once. But somehow now we want to compute the Euclidean distance between each pair of rows between these two arrays. So that is, you can consider that now a row of x is represented using this way, x0, x1 until xd minus 1. This is only one row from x. Of course, it should have d elements here, right? And similarly, we represent a row of y by another d numbers, y0, y1 until yd minus 1. This is just we extract one row from x, one row from y, then the Euclidean distance between the two rows should be computed using this formula. Right? According to the Euclidean distance definition, it should be the square root of the sum of the square of their difference. Like that's x0 minus y0, this difference square, then plus the second dimension x1 minus y1 square until you get all the sum and then do the square root. This is only one distance. One distance is that you get one Euclidean distance between one pair of rows from x and y. And note that what we want is the Euclidean distance between each pair of rows of x and y. So for any row from x, for any y from y, we want to get the Euclidean distance. Here is an example so that you can more understand what I'm talking about. Suppose x is such a shape 3-3 array, and x has the numbers like this, and y is another shape 2-3 array, and y is something like that. In this case, how many distance values do we need to compute? 6, right? Because x has 3 rows, y has 2 rows. So in total, we need to compute 6 distances because for each row of x, for each row of y, we want to compute pairwise distance. So in total, 3 times 2, we have 6 distances. Then consider a more general case. If x has shape m3 and y has shape n3, how many distance values do we need to compute? In this case, it should be m times n, right? Because for each pair, we need to get one Euclidean distance. Then we consider okay, for this general case, we need to get m times n distances. Then we should store these distances in some array, right? What should be the shape of the output array? How to arrange these Euclidean distances so that we can easily say, okay, from some output, we can say okay, this entry corresponding to which row from x, which row from y. In this case, we consider we store all the distance values in an array called output. And the convenient way is that we let output ij represents the distance between xi and yj. So xi is one row from x, yj is one row from y, and for this pair of xi and yj, we store the output ij. So basically that means after we computing, we should get an output with exactly the shape m by n, and each entry of output ij represents such meaning. All right, basically now at least we get our output very clear. We know what is our input. Our input is x and y to arrays, and what we want is an output has a shape m times n, so that each entry output ij represents such thing. Then of course we need to do some computations between x and y, right? So that we can implement such formula. Of course, we need to first think about can x and y be broadcasting, and we already know, for this example, absolutely no. 3-3, 2-3, they are not compatible. They cannot be broadcasting together. In this case, the computation might be more complicated because if they cannot be broadcasting together, then how should we make sure that all the computations can be done in some element-wise manner? Actually, we need to one more extra step because first we want to make sure that x and y can be broadcasting together after maybe some reshape operation. Right? Basically, is that we try to manipulate their shapes until they can be broadcasting together. But of course, in the meantime, they should be meaningful to do such reshaping. All right, we get one clue here. Try to do reshape and try to make them compatible. So before we going into the actual steps, I would like to talk more about this task itself. That's the pairwise distance. This task, pairwise distance, actually is quite useful, and we do it frequently in AI and in machine learning. Because you can try to imagine that actually x and y, there are two data. Specifically, you can think X is a training data. Y is a testing data. Of course, the training data and testing data, typically they don't have the same number of data points, right? For example, here X has M data points, Y has N data points. So of course, the number of data is different, but since they are like the data for one task, they must have the same number of features. So that's why the number of columns D must be the same in X and in Y. Typically, we say that this D is a number of features. Of course, they should have the same number of features, but they don't have the same number of data points. Then the meaning of pairwise distance of such X and such Y, basically it means that now we have two data sets, X and Y, possibly training data and testing data. We want to compute the pairwise distances between training data and testing data. So this is the practical meaning to do this one. And later on, when you are learning the k-nearest neighbors and when you are learning the k-means clustering, you will find that we are always doing such things to compute the pairwise distance between training and testing data. All right, so yeah, at least you have the motivation to do such thing because definitely you will make use of these operations. Then go on with that one. How can we make X and Y be broadcast together? How can we try to reshape a little bit to manipulate their shapes? This is what we do. We reshape X so that it has the shape 3, 1, 3. Basically, we insert one new axis in the middle. Then for Y, we reshape it to be 1, 2, 3. We insert one new axis at the beginning. After that, can this reshape X and reshape Y be broadcasting together? Yes. Yes, now they can, right? For all 3 dimensions, they are compatible. Then you may think that is some like arbitrary random reshaping thing so that we only need to make sure they're compatible. No, it's not arbitrary. It's by design. We design them to be in this way because in this way they have some practical meanings and all the following computations have practical meanings. So now they can be broadcasting together. So we can do some like array mathematic operations. We do this thing. We let the diffs be reshaped X minus reshaped Y. This is the first step of computing Euclidean distance, right? To compute the Euclidean distance, you first need to get the difference between the two arrays. Then the shape of these diffs is 3, 2, 3. According to broadcasting rule, we can easily get that, right? It should be the maximum size of all the dimensions, 3, 2, 3. But what is exactly in these diffs? Here we make use of some visualization so that you can like see that more clearly. Originally, we have this X, 3 by 3, right? These are 3 rows. After reshaping, X is reshaped to 3, 1, 3. So here we consider that the visualization follow this rule. Now the axis 0 represents the layer, and axis 1 represents the row, axis 2 represents the column. This is a typical way to do visualization. You may have your different ways, but just make sure that you are consistent. That would be fun. So here we just follow the convention, visualize in this way. And to show that it's some 3D array, like it has some layers, we use some gaps here to represent they are in different layers. So now they are not in the same layer. All right, 3 layers. Each layer has 1 row, and each row has 3 columns. This is the reshaped X, right? So basically, from X to reshaped X, you can see now the first row is extracted to be in the first layer. The second row goes into the second layer. The third row goes into the third layer. So now this reshaped X arranged in this way, like 3 layers in a 3D space. Then what is this Y? Originally, Y has this shape 2, 3, 2 rows, 3 columns. We reshape it to be 1, 2, 3. 1, 2, 3, basically now it becomes some 3D array with only 1 layer. inside each layer, it still has 2 rows and 3 columns. So basically, it looks very similar with this Y. The reshaped Y and Y look very similar, but still we use some space here to represent it's a 3D array now. So even though it only has 1 layer, but it has such layer dimension. All right, reshaped X looks like this, reshaped Y looks like this, and we get the diffs. The diffs is reshaped X minus reshaped Y. According to broadcasting rule, all of this reshaped X and reshaped Y will behave as if they have the shape 3, 2, 3, and they need to copy itself along some directions, right? So basically that after expanding or after copying itself to be in the shape 3, 2, 3, reshaped X will behave as if it's something like this. From 3, 1, 3 to 3, 2, 3, we find that it should copy itself in the second dimension. Or basically it means that each row should copy itself twice, so that it makes as if it has 2 rows in each layer. So now the reshaped X behave as if it's like something like this. The first layer, now it should have 2 rows, but the 2 rows are exactly the same because it copied itself along this dimension. And the second layer, third layer, they're all like this. Just the row copy itself so that it behave as if it has 2 rows. Just as if, not really become 2 rows, but just behave as if. Then what is this reshaped Y behave? This reshaped Y, it will also behave as if it had the shape 3, 2, 3. And we find that from 1, 2, 3 to 3, 2, 3 basically means that it should copy itself along the layer direction, along the axis 0, that dimension, right? So that means reshaped Y has 1 layer. It simply copy itself to second layer and to third layer. Behave as if it's an array like this, 3 layers, but each layer has exactly the same value. All right, so if we want to do this reshaped X minus reshaped Y, basically we will do some element-wise subtraction between these 2 arrays. Then let's check what is in these diffs, this resulting array. We check them layer by layer. So layer 0 is this array, subtract this array, right? And for this array, it has 2 rows. The first row, it comes from x0. If you try to get this one is exactly from this one, right? So basically, it's x0 minus this row is y0. This row comes from this row, y0. Then what is the second row in layer 0 of diffs? This row. This row, again, is x0, comes from that x0, minus this row. This row is y1. This row comes from here. So that means, okay, in this array diffs, the layer 0 maintains such value, x0 minus y0, x0 minus y1. Then what is in layer 1? Layer 1, if you try to do this mapping, you find that, okay, in layer 1 of x, basically they both come from the x1, this row, because this row copied it to be in the second layer. And then for the second layer of y, this reshaped y, so basically it's still original y, right? Because all the layers, they are the same in the reshaped y. So we can see that, okay, now the layer 1 of diffs actually maintain the values x1 minus y0, x1 minus y1. And then I believe you can similarly get that actually now in layer 2 of diffs, it maintains the value x2 minus y0, x2 minus y1. If you just try to compare these 2 reshaped arrays with the original arrays, just try to get, okay, where this data come from, you will get that. So it is important to see that where such broadcasting, actually each diffs ij stores xi minus yj. So now each layer in this diffs actually is the pairwise difference that we want. The pairwise difference between a row from X and a row from Y. Like basically, they store all these things. And for each entry, not entry, actually for each row, diffs ij is one row. For each row, diffs ij just stores this xi minus yj. So through reshaping in this way and through such broadcasting operation, actually we get the pairwise difference. This is what we want, right? Recall the Euclidean distance. The very first step is that we get pairwise difference. Only after you get this pairwise difference, you can do the square, you can do the sum, you can do the square root. So this is the first significant step you want to get Euclidean distance. So if you can get the diffs like this, then basically all the following things will be quite straightforward, right? We just follow the formula of Euclidean distance. The next step is, of course, we want to do the square. So by the way, if you print these diffs, you will get something like this. It has the shape 3, 2, 3. And exactly the diffs ij stores xi minus yj, so like this. Here we just use one line of code, but also you can try to separate them one by one. The first step is that we try to do the square, use the diffs, like do this square so that, okay, now all the pairwise difference gets squared. And then according to Euclidean distance, we need to do the sum. For this sum, the only thing you need to make sure to get correct is the axis. Like which axis you want to get the sum. If you consider these diffs, we know that diffs ij is such xi minus yj, right? Basically, we want to add all the elements of such column direction together. So the column direction represents the axis 2. We want to get the sum along that direction. So here, that's why we need to use this numpy.sum diffs square axis equal to the column axis along that direction. Basically, that we want to add these things together, like minus 0.11 plus 1.27 plus 3.45. This is the sum. And for each row, we want to get the sum. And the row is the column direction. Last step, quite simple, just use the square root, numpy.square root of this sum. After that, the this, if you print the this, you get this thing. And this is already the output we want. And of course, the shape must be 3, 2. It contains 3 rows, 2 columns. In total, 6 distance values here. And each entry of this ij represents the Euclidean distance between xi and yj. So this is another example. This example is somehow a little bit more complicated than the previous one, but still, to work it out, the key part is to use broadcasting. That is how to get the diffs, right? After you get the diffs, all the following steps just straightforward. Key part, how to get the diffs. Of course, if we want to do it very conveniently, just use this broadcasting. But a little bit tricky here is that before broadcasting, you need to get them to be reshaped. Only after reshaping they can be broadcasting together. Otherwise, you cannot do that. Some questions may be leave to you as some like after class practice. Like if I ask you to write a program, rewrite the program, but without use the reshape function, you can try to think about how to use numpy.newAxis and numpy.expand dims to do this thing. So basically, just replace the reshape steps with these 2 functions. I believe you can do it if you already know the syntax of these 2 functions. All right, so any question regarding this example? Yeah, I think this example, it may take some time to absorb all these steps here. That's why we just make everything very clear, like make all these visualizations very clear. So especially that if you are working on such broadcasting problems, in the first time or maybe the first several times, it's good that you try to visualize them. Actually, it's good. Of course, it costs you some time to do visualization, but it's good to do that because after you get familiar with this broadcasting, maybe in the future, then you don't need to do such visualization anymore. But still, at the beginning, you can try to visualize them. All right. If no question, then basically we finished it. All the contents about NumPy. We only left the last part about why the NumPy arrays are better. So like after introducing so many things about NumPy, then why should we use NumPy arrays? Right? Still, I need to let you convinced that actually you really need to do this NumPy array instead of just using the list. Before learning NumPy, I believe you already can do many things using the Python list. So here, motivate you that please use NumPy array instead of the list. So specifically, NumPy array has 3 advantages over the Python list. First, it consumes less memory. Secondly, it's fast compared with the Python list. Thirdly, it's more convenient to use. And we will use some examples to illustrate that. First, about the data memory. Note that for NumPy array, it contains one single pointer to one contiguous block of data. But the Python list contains a pointer to a block of pointers, and each of which points to a full Python object. So here is like try to see like how they store data. For NumPy array, usually it has some head. This is their object head and then the data. Note that the data only needs one single pointer to this block of data. One data point is enough. But for the Python list, after this head, like for all these items, it contains one pointer to a block of pointers. So this pointer points to a block of pointers. And each of the items actually needs to have another pointer to this data. So that's why the Python list consumes much more memory than NumPy array. And we can use such example to show that. So here we import NumPy and some system, and also this GC system, GC library is used to like calculate the memory. And now we define such a method, actual size, so that we can calculate the size of different objects. And after that, in this exercise, actually we basically want to get this size of input object. Then let objects, this new value be this input object, a list of this input object. And then while these objects, for each element in these objects, we just add it and let this memory size added with this obj size, and at last we can return the memory size. It's okay if you don't know the details of this function. This is just an example to illustrate that the NumPy consumes less memory. And we create a list, L. L is a list from range 0 to 1000, containing 1000 elements, and A is the NumPy.arrange 1000. Basically, L and A, they contain the same elements. Like both contain 1000 elements, right? Then after print the size, we find that this L, the list, actually consumes this bytes, this number of bytes. That's 37,000 bytes. But this A, this array, only consumes 8,000 bytes. As we can say, actually the list for 1000 elements, if you want to store this 1000 elements, the list costs much more than an array. So this is one advantage that motivates you to use the array because it consumes much less memory. Then the second advantage is about the time comparison. The NumPy array is always like more efficient than this list. So again, we try to create a list and an array with the same size. Let list 1 be range size. Here size we define here. Size is like 1 million. We want to create some 1 million length list, and list 2 is another range size. Then we declare the arrays. Let array 1 be numpy.arrange size, array 2 be numpy.arrange size. And then we try to capture the time. We want to calculate what is the time doing these computations. Here we need to use such library time. Simply import time as t, and then capture the time to be initial time. Simply you use this function t.time, then it will return the current time, which is very convenient to use this module. And then we multiply the elements of both lists and stored in another list. Note that if we want to do this, we need to use the list comprehension and this zip method, the parallel iterations. So result list be A times B for AB in this zip list 1, list 2. And after we done this, we capture the time because we want to calculate the execution time. So the time taken by the list, let this t.time, the current time, minus the initial time. And we get that for such operation, that the element-wise multiplication of 1 million elements using list, it costs 0.13 seconds. Of course, you will see that, okay, 0.13 seconds seems still very fast, right? But if we try to compare it with the numpys, you will see that the same operation, but now you use the computations in NumPy, only cost 0.006 seconds. So which is like much more faster than the list. Especially that if you have more data points and they have like higher dimensions, the NumPy list, the NumPy arrays will always be more efficient than lists. Third advantage is about the effects of operations. So that is the NumPy array actually are much more convenient than the Python list to use. Here we create a list, just 1, 2, 3, and then let the array be numpy.arraylist. Convert this list into a NumPy array. Then we try this thing. We let ls be ls plus 4. Basically, we want to add 4 to each element of list. And we will try this. If it not work, then we will raise such type arrow, like print this list don't support list plus int. And then we will try on an array. So again, we let the array be array plus 4, add 4 to each element. Of course, after you learn broadcasting, you know that this definitely work, right? Definitely, like if you add an integer to an array, definitely work through broadcasting, and we can print it. So the output of the above code cell would be list don't support list plus int. But the modified NumPy array, it can do this and can get 5, 6, 7. So that means if you want to perform some like operations, arithmetic operations, basically use NumPy array will be very convenient because it has the broadcasting mechanism. But if you cannot do the same thing for the list, for example, you cannot like directly add an integer to each element of the list using this one, you need to write the list comprehensions. Like you need to create a list from the original list using list comprehensions using a for loop inside that comprehension. So this is the third advantage of NumPy array. So later on, when you are trying to like make your own AI models, try to implement your own machine learning models, try to use NumPy arrays. Always try to use NumPy arrays, especially if it involves the mathematical operations. All right, so at the end, we also leave some practice problems. So still you are recommended to first try to solve by yourself. After that, you can try to check your answers with the solutions we appended here. To make sure that you get like everything correctly, make sure that you can understand all this content here. So that's all about the Advanced Python Programming lecture. I know it's quite a long lecture, and we spent lots of time in this. It seems that now it becomes a Python programming course instead of an AI course. But finally we finished it, and later on we can do some real AI things because I believe now you are all equipped with this necessary contents. Now you are getting well prepared to implement your own AI models using the Python programming. And I guess probably this would be the last semester that we teach this additional lecture on advanced Python programming. Because later on, the prerequisites of 2211 becomes 1023, and these contents will be taught in 1023. So later on, actually, like in the next semester, possibly I don't need to teach all this anymore. Let all the students who learn that in COMP 1023. All right, any questions so far regarding this lecture? Great, yeah. Then, yeah, congratulations, we are done with the Python programming this course, and we can now turn into the AI course. So let's take a 3 minutes break. After the short break, we will start with the naive Bayes model, our first AI model. All right, yeah, the break is so short. So a little more add-on about this example, the pairwise distances. I know that it's very hard to think of these two steps. That is why should we reshape in this way, right? Of course, after we know we should reshape in this way, maybe the following things will be relatively more natural. But how to think of this one? Of course, after I introduce this example, you should like get some sense that later on, if you meet some similar examples, similar things, you should do this way, do this reshaped way. But here is some like motivation about like doing this way is that if we consider the pairwise distance here, x has 3 rows, y has 2 rows. Since now we need to compute the pairwise distance. Basically, that means for each row of x, it should be used twice. The first time it's used is that it will be used to subtract the first row of y. Second time it used was this row should also be used to subtract the second row of y. So each row of x actually should be used twice, right? If we want to get the pairwise distance. And then similarly, each row of y should be used by 3 times because it should be used to be subtracted by each row from x. Alright, so at least we get some hints that, okay, each row of x used twice, each row of y used 3 times, and we know that after broadcasting, basically it will copy itself. So that means we need to think about some reshaping way such that for each row of x, it should copy itself for twice along some dimension. And for y, after broadcasting, it should copy itself for 3 times along some dimension. And of course, this dimension should always keep the elements in the row unchanged because what we want is that we extract a row. So basically, that is the last dimension must keep the same because the last dimension we always want to let it remain the row, right? The row is still the row. So we know that if we see it as rows and columns, and then in 3D we view it as layer, rows, columns, then basically if we want to let the row remain the row, that means the column dimension must still be the column dimension. Or actually that means the last axis after reshaping must be in the axis 2, the column dimension. So that's why actually after reshape, we won't change the last one. The last one, we still let it remain the same, like keep the same size 3. And then for x, we want it to copy itself for twice. So that means we want to make it compatible with the size 2 of y here. That's why we insert the axis here. So that, okay, now in this axis 1, x has a size 1 so that it can copy itself for twice to compatible with y here, y size here. And similarly for y, we want it to copy itself for 3 times because it will be used for 3 times to do this difference, right? So that means we want to increase a dimension here to be compatible with x size. So that, okay, now after broadcasting, it should copy itself for 3 times so that it can compatible with x size in the axis 0 and copy itself for 3 times. This is some hint that why we insert the axis here, insert axis of x in the middle and insert axis of y at the beginning. Of course, if you do some other ways, that is, if you reshape x to be 1, 3, 3, and somehow you reshape y to be 2, 1, 3, actually it also works, but the output shape will be different. The output shape basically is that after you do all these things, you need to do some transpose. If you want to make sure that the output ij represents the distance between xi and yj. So that is basically if you insert an axis at the beginning for x, insert an axis for y in the middle, and then you do everything the same, but at the last you will get an output with the shape 2, 3. And then you simply do a transpose to get the correct answer. Alright, so that's some clues about why reshaping in this way. Of course, the important thing that you must keep the last dimension still the last dimension because basically that means the rows. Alright, next we will start with real AI lectures. Non-U-based classifier, start with this one, which is a very classical machine learning model. Then we need to know some fundamentals of machine learning first. What is machine learning? Actually, in the introduction to AI, we already mentioned a little bit about that. So machine learning is the science and engineering of getting computers to act without being explicitly programmed. Let the machine learn by itself. And there are 3 types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Note that in this course, we only cover supervised and unsupervised. Reinforcement learning, we won't cover, but we will provide you with some materials for your self-study. This figure basically illustrates the differences. Like supervised learning is that you give some supervision to your machine. For example, you may say that, okay, now a cube has 6 sides that are square, and then the robot or the machine understand that, and okay, now it knows how to classify the cube with non-cube. And for unsupervised learning, you won't provide any information, you won't provide any supervision to the machine. Basically, you give all your data to the machine. And the machine will try to group different data. Like the machine does not know what is this. The machine doesn't know, actually it's called cube. The machine only knows that, okay, these look like groups. At least these items are different with those ones, so maybe try to separate them into different groups. Like previously when we were doing the Mentimeter. The Mentimeter had that function, right? Grouping different answers is try to use this one. Then reinforcement learning, basically it's you let the machine to learn some actions for different situations. Usually that's a series of actions. So the machine is not trying to do any prediction. The machine tries to execute an action to perform some task. For example, possibly this task is that you just give the machine an item, let the machine to put the item into some holes that match, and then the machine will just try different actions to say, okay, does this work, does that work? So this will be the differences among the 3 types. Then specifically for supervised learning, we need to form a training data set. This training data set must consist of examples with inputs and correct outputs. Here we call the correct outputs as labels. This is a terminology we use in machine learning, labels. So that means whenever you give a data to your machine, you need to tell your machine the correct label. What is this data belongs to? Like this is what we call supervision. So you already tell the correct answer to your machines, provide all the labels. And this training data set is called a label data set when we use supervised learning. And then this label data set is used to train a machine to yield desired output. So that is allowing the machine to learn the relationship, or we say the mapping between inputs and outputs. Basically because you already give like the inputs and the labels. Then the machine just tries to learn, okay, the relation between the inputs and the labels, so that later on it can use the relationship it learned to do prediction for some new data. Then we can further divide supervised learning into 2 types. Classification. Classification is classify the data into the categories. The categories, we also call it classes, represented using the different labels. So you may see that actually we use these terms interchangeably. Category, class, and labels. Basically, they just refer to the same thing. And this class is not the Python's class, by the way. Python's class is the OOP concept. This class means the class, the common sense class. For example, yes or no are 2 classes. Positive or negative or neutral, 3 classes. And this is usually used to do the sentiment analysis. That is given a text, let the machine to predict what is the sentiment. Usually this task is used in some review platform. For example, in some movie platform, after you watch a movie, you can write some reviews, right? For example, maybe you like the movie, maybe you hate the movie, you write some reviews, and then the machine can be used to predict, according to the text, according to the review you write, to predict, okay, whether your sentiment is positive or negative or neutral to this movie. This is called a sentiment analysis. Actually, sentiment analysis is just a classification task. Try to classify the data into 3 classes. Another type is called regression. Regression is give a real or continuous value as output. In regression, still we have the label concept, but the label is not classes anymore. The label is some continuous number, continuous value in a range. For example, to predict salary based on work experience and to predict the weight based on height, etc. We know salary and weight, basically they are some numbers in a continuous range. They are not the classes anymore. Here is an example demonstrating the idea of the supervised learning. So suppose now we want to train our machine to do some math. And instead of explicitly programming it, we use machine learning idea. So we pass a set of input data and the corresponding answers to the machine, and then we ask it to figure out the relationship between the data and the answers. Like here, we have 8 some math formula, of course incomplete ones. We don't know what is the operations because we want the machine to learn that. In total, we have 8 data samples, we can see that. Then for this one, what is the training data set and what is label?
The label is the right-hand side of the equal to, and then the training data is on the left-hand side.
Yes, correct, very good. Training data basically is off in the left hand, like 2, 4, 5 is a training data point. 5 to 8 is a training data point. Like actually we can see that for each of the data it has 3 features, right? And then the label is a correct answer here. Like the first data point has the label 3, the second has the label 2, so on and so forth. Very good, you already get what is training data, what is label. Then can you figure out the relationship between the data and the labels?
Times and then minus.
Yes, correct. Okay, very good. Yeah, very good. You perform this supervised learning very well. Give you some supervision and you already figure out the relation. Okay, excellent, like supervised learning model. Great. Yes. So this is just an example to illustrate what is supervised learning. Basically, you give data points, labels to machine, let the machine learn the relationship, so that later on when you give some new data, for example, later on you may give some new data like 10, 9, 12, right? And then let the machine to predict, okay, what should be the output. Basically, after the machine already learned the operations, it should calculate the correct one. All right, then let's see some real-life applications of supervised learning. Basically, like all this classification or regression tasks, we see that they use the supervised learning, like the image classification. Image classification, for example, the Facebook can recognize your friend in a picture from an album of tagged photos. That's the classification. And the visual recognition, the ability of a machine to identify objects, places, people, actions, and images. This recognition actually also uses the supervised learning. Signature recognition, when you buy something and you need to pay, for example, maybe you pay by the automatic bank checks. Usually it asks you to write some digital like signature, right? Then actually this bank system will do the automatic signature recognition and then try to identify your handwriting and then try to like recognize, okay, what is this signature and whether it's matched with the signature is stored in the system. And spam detection, like in your emails, maybe you will receive like lots of spam emails, some phishing emails, but now like all the email services actually they will provide such spam detection to try to flag some emails to spam, to junk. For example, the Google has now advanced to the point that it can detect and filter out spam and phishing emails with about 99.9% accuracy. But it just is claimed if you use the Gmail, maybe you can also like sense by yourself. And actually the weather forecasting will also make use of the supervised learning. Like Hong Kong Observatory, yes, it predicts that, okay, possibly tomorrow it will raise the typhoon signal, right? All this like forecasting actually incorporates the machine learning in strengthening the the techniques in monitoring and forecasting. So all like these ones, actually, they use some supervised learning techniques. Then let's see what is unsupervised learning. So here we use unlabeled data set. Note that for unsupervised learning, you still need to give the training data. If you want to train a machine learning, like you always need to pass some training data. But now, the training data is unlabeled data set. So that is without giving the correct outputs. You simply train the machine to learn on themselves. You never tell the machine what is the correct answer. Then the machine tries to find a pattern in the unlabeled data and respond. Because now it does not know the correct answer. So it can never learn the relationship between the input and the correct output. But no worry, the machine is very powerful. It tries to do some pattern recognition to find a pattern so that, okay, after extracting the pattern, it can try to do some grouping things. So this would be further divide it into these two groups. The first is clustering. Clustering simply group the data into clusters that are similar between them and are dissimilar to the objects belonging to another cluster. So for example, finding out which customers made similar product purchases. This is a clustering task. Like when you buy something, like when you do the online shopping, for example, in Amazon, in Taobao, and actually the platforms will try to extract all of like your data, like your purchase history, something like that, and then try to cluster the customers. So try to group the similar customers together. Like if you and your friends buy some similar product, then possibly you will be in the same cluster. By the way, do you know why this platform needs to do this thing, this clustering thing? Yes, for advertisements, yes. And these platforms, actually, they do advertisements by personal recommendation. It's not recommending the same item to all the customers, right? It's personal recommendation. Basically, the personal recommendation is based on these clustering results. For example, if the system finds that, okay, you are in such a cluster, and for the customers in such cluster, they all like one item, then possibly the platform just recommend this item to you because it thinks that, okay, you are highly probably also like such item and very likely to buy it. This is the clustering. Another group of unsupervised learning is called association. So here is a rule-based machine learning to discover the probability of the co-occurrence of items in a collection. Here the key is finding some co-occurrence. For example, finding out which products were purchased together and try to group these products like together. And usually, this is also used for personal recommendation in the platforms. For example, I don't know whether you notice it or not. After you buy something in the online shopping platform, it will jump out the advertisements. After you pay that, it will jump out that guess you also like. Basically, this guess you also like these items are based on what you bought just now, because they find that, okay, actually these products, they will usually purchase together. So after you buy one, possibly you will need another one. This is called unsupervised learning. Again, the same example demonstrates the idea of unsupervised learning, but somehow since it's unsupervised, we do not provide labels to the machine. So we want to train machine to do math. We pass the input data, but not the corresponding answer. And then we ask the machine to figure out the patterns from this data set. This is just the idea of unsupervised learning, but you may think about this question, like for this example, is it a suitable task for the machine to learn the patterns? No, definitely no. You give machine these 8 data points, basically the machine knows nothing. The machine does not know actually you want it to do some math, right? It will never figure out, okay, how to do the math operations. So yes, so for unsupervised learning, you need to try to use it in some suitable tasks. The suitable task for unsupervised learning is try to find patterns, try to group similar items. But if you want to do some like task that requires a correct answer, like doing math, requires the correct answer, basically unsupervised learning is not suitable. Yeah, very good that you already like get these ideas, already find that it's not suitable, definitely not suitable to do this. Some real-life applications of unsupervised learning, like the semantic clustering, like semantically similar words share a similar context so that we can group these similar words together. And we can also try to group the images or videos based on their similarities and group audios based on the acoustic similarity. And also we can use unsupervised learning identifying accident-prone areas. This is a real-world application. Like it can be used to identify the accident-prone areas and then introduce safety measures based on the intensity of those accidents. So for this task, actually you don't need to provide the supervision. You don't need to provide the labels, but you only need to store like for example, which areas are accident-prone ones. And actually, basically, it will try to use this one, which is called association, to try to get some co-occurrence and try to predict that. So we can try to compare the supervised and unsupervised learning in a table. This summarizes their differences. First, the training data, they already differ. Supervised learning requires labeled data. And note that in this labeled data, we always need some domain experts to label data. Of course, you will see that the AI can label the data. Yes, the AI can label the data, but usually after AI label the data, we will by default assume that it's not 100% correct. Usually, we still need some human experts to examine like the data labeled by AI. And for unsupervised learning, much easier. Unlabeled data, you don't need anyone to label the data. You just need to collect the data. And for categories, supervised learning have classification and regression tasks. For unsupervised learning, it has clustering and association tasks. For preference, the supervised learning is preferred if we want to calculate outcomes. We want some outcomes as the prediction, then we use supervised learning. For unsupervised learning, the preference is to discover some underlying patterns. Possibly we don't care about outcomes, we only care about some underlying patterns. Training time of supervised learning is usually shorter, but training time of unsupervised learning usually is longer. This is, you can think about that because for supervised learning, basically we are learning the relationship between data and label. Right? So basically you just need to learn such relationship, such mapping. And for unsupervised learning, since you are discover underlying patterns, you are not like trying to learn these things from the data one by one. You are trying to compare the data point with each other data point to get the underlying pattern. So that's why the training time of unsupervised learning is typically longer. Accuracy. Of course, supervised learning has higher accuracy. It has supervision, right? Then for the optimal strategy, the supervised learning depends on the data and the learning algorithm. But usually we see that the unsupervised learning optimal strategy only depends on the data. Last, the algorithm of these two different learning. For supervised learning, we have naive-Bayes model, KNN, decision tree, linear regression, logistic regression, and support vector machine. For unsupervised learning, we have k-means clustering, hierarchical clustering, and a priori algorithm. But note that those algorithms we listed here are all shallow models, or they are models that does not involve the neural networks. Usually, if it involves neural networks, generally it belongs to supervised learning because for training neural networks, we need to provide the labels. So here we exclude the neural networks, just list some shallow models. Those are all very classical machine learning and AI models. And in our course, supervised learning, we will learn the naive Bayes and k-nearest neighbor. For unsupervised learning, we will learn the k-means clustering. And by the way, actually, the department suggested that we should delete k-nearest neighbor and use the linear regression instead to update the course syllabus. Even though I'm not very sure about the reason, but I guess maybe probably from the next semester, the KNN will just be deleted from this course and will be like adding this linear regression instead. But for this semester, we're still learning KNN. All right, this is about comparison between the two different types of machine learning. Any questions so far? Great, if no question, then we can end here today. So next class, we will go into some practical problem and try to solve it using the net-based model. So please remember to attend the lab 2 on next Monday, and next Tuesday, we will take your attendance. Okay, so see you in next class.